everyone. My name is Muhammad Iman Hafizudin and Kamal Azman. So today we're gonna walk through our project called File System, which is a command line exploration of free space management in file system. But first thing first, I will introduce my group member. We choosing topic 9, which is free space management, and it consists of our group leader, which is Nasrin, and Natandra, and also Dila Nevada. Lastly is me. So for title and abstract, this project is all about understanding how operating system manage free space using 4 different techniques, which is bitmap, linked list, grouping, and also counting. So basically, we built a simple Python-based simulation that lets user interact with these methods and see how they handle space allocation in real time. It's like a hands-on way for students, especially for us, which is studying in computer network and security, to get a clearer picture of what happened behind the scene when managing this space. So we proceed to introduction part. So if you have ever thought about how your computers know how where to store your file on a hard drive or SSD, that's where file system come in. And the way they are handled free space is crucial. If free space is managed well, your system runs smoothly. If not, things can get messy with fragmentation, slow access time, and also waste space. For this project, we focus on 4 common way to manage that free space. This is bitmap, linked list, grouping, and also counting method. This method each have their own pros and cons, and we build simple command line tool, which is our intimate file system to let user experiment with them. By interacting with the simulation, you can see how space is allocated, free up, and how each method work in practice. So for problem statement part, now the problem is that while these free space management techniques are important, a lot of the time they are taught just in theory. So you only get the concept, but it's hard to picture how they really work. So if you just reading about them, it's tough to see how things play out in real operating system. This is where our project came out, which is by system. Instead of just talking about this method, we want to give students chance to see them in action. Our goal is to make it easier for people to understand how this method impacts system performance and storage efficiency by letting them interact with the system and observe the result in real time. So that's all from my part. Thank you.
So for the latest works, we look at other OS learning tools such as EDOS, and we find a clear gap because these tools they tend to focus on memory management and file allocation, but they did not include the free space management techniques. And while there are a lot of resources that can explain this theory online, there are no interactive tools that can clearly demonstrate how this technique works whenever we save or delete a file. So our project aims to address this by offering a focused simulation environment that runs right in the terminal without needing a complex graphical interface. So how we do that is first we do our research, we study the modules. For example, this module of OS concept by Shilberschatz, A. Galvin, PB, and Gagner, and also the slides provided by the lecturers in order to have better understandings on free space management methods, including their advantages, limitations, and real-world usage. After that is data structure planning, where we decide how to represent each technique in code. For example, to represent a bitmap, we can use binary values, and to represent a linked list, we can use nodes with pointers. The next is user interaction design, UI design. So we define how the user can interact with the simulation, how they allocate and or free the blocks, and how they can reset the system. We also plan the visualization strategy. So we use green to indicate free blocks, and we use red to indicate use blocks. And then we use arrows also to represent links or group transitions. And then finally, we use phase prototyping, where we start with just one technique we tested it until it is perfect, and then we add other techniques. So this keep the code modular and separate, making it easy to debug. And then after development, we run comparative testing to observe how each method handled the same task, making the trade-offs between them visible. And next is the design and implementation. So the simulation we choose to develop as a modular command line program using Python 3. So the interface is purely text-based. We use ASCII symbols and emojis for visualization. And the key design choice here is modularity, where each management technique is implemented in its own separate file in order to keep the code clean and reusable. So the structure is reflected here in our plan file structure. So the DSIM is like the menu, the heart of the program, how we navigate between each methods. And the other file is to demonstrate how each management technique works. So bitmap only in bitmap.py, linked list only in linked list.py, and so on.
Okay, so now we are going to do the project demo for the application. So using the DSIM.py is the main menu where we should run it. Okay, so after running it, we are greeted by this menu. 1, 2, 3, 4, 5. So first one is to open the bitmap. Second one is to open linked list. 3 is for the grouping, 4 is for counting, and 5 is for exit. And as you can see, when I press bitmap, it will open import. As you can see, bitmap, this one. And when I open linked list, it will open from linked list. When I open grouping, it will open from grouping and then from counting. So let's do it. Two simulation method. So first one is the bitmap. Okay, and then after that, we are greeted by this menu. We can choose from 4 of this. So this is the state. Green means that it is empty or free. So let's allocate a block. Number of blocks allocated, let's say 3. Now, as you can see, 3 is now occupied or allocated. And then we can try to allocate another one, maybe just 1. Now it's 4. And then we can try to free the blocks. Free, start index to free, so we can choose index 1, number of blocks, and then I want it 2. So now, as you can see, from index 1, so it's starting from index 0, 1, 2, 3, 4. So starting from index 1, this one, it's remove or free 2 of the blocks. So as you can see, 2 of it's gone. So let's try allocate another block, 2. So it's occupied again. We can try free again from index 2 now. Number of block 1. So now index 3 is gone. We can try from 0, 4. Now all of it is done. And then we can go back to main menu. I'm just gonna make this bigger. Main menu. And then I'm gonna choose linked list. Okay, so it will show us the disk, which is still empty, and then linked list is also still empty. So we can allocate the block now. So 1 is choose. We for linked list we can choose like the amount of blocks we will allocate. So it's gonna be 1 by 1. So allocate again. As you can see, it keeps adding up 1 by 1. And linked list also like this. So and then free. See, remove it by 1, by 1, by 1, by 1, by 1, by 1, and back to 0. Or we can free it all by using number 3 preset. So I'm gonna add the bunch. Instead of pressing 2 1 by 1, you can press 3, and now it will reset it back to default, which is all free. And then I'm gonna choose 4 to back, and then the next function is grouping. So the disk is empty or green. Groups, this showcases the group, and allocate group 3 blocks. So it's allocating by 3. So as you can see, index 0 to 2 is occupied now. it will keep adding by 3. As you can see, 3, 3, 3, 3, 3, all in total is 15 blocks. So free last group, it will free, the group is 3, so we will free 3 blocks. So as you can see, add free. Okay, and then also we can reset it. Instead of removing the group one by one, we can remove it all by clicking on reset. Bam, all of it is now gone, back to 0. So for the next one, I'm gonna choose counting, the next function. So counting for, okay, so this is the allocation start count. So this shows the starting index and then the count, how many will be counted inside the group. So first one, I'm gonna allocate the blocks, enter number of blocks, I want it 2. So as you can see, this is the index 0, and then 2 will be the amount or the count. So maybe another one, 2, number of blocks 6. So as you can see, this is from index 2, and then it will add another 6 or a group of 6, and I can allocate another block. Maybe I want it 10. So as you can see, from index 8, and then the amount is 10, the count, and then I can free it, choose 2. So the group 3 is removed now, only these 2 group, and then I can free it again. As you can see, expect, and maybe I can try to allocate it. So maybe 10, and then 5. Okay, now for the third function is reset. We can reset it back to the default state, which is all 3. So now it's all done. I press 4 to back, and then 5 to exit. Exiting file sizing. Goodbye. Yeah, so that's all for the demo. Thank you.
Now for future work and conclusion. So while the file size sim provides a robust foundation for understanding free space management, several enhancements could elevate its educational and practical value. For one, the advanced fragmentation visualization. So currently the visualization is basic. So for future iteration, we could introduce more nuanced visual cues to highlight different types of fragmentation, like internal versus external, and illustrate their impact more explicitly. For example, using different shades of red for different allocated processes, or visually fragmented of free space. Next is the performance metrics and comparison itself. So essentially adding allocation or deal allocation time and metadata overheated for quantitative comparison. So this would provide a more data-driven understanding of their efficiency trade-offs. Next is the dynamic disk size and block size. So allowing users to define a total disk size and individual block size would make the simulation more flexible and enable experimentation with different system configuration. Next is the randomized allocation pattern. So introducing options for randomized allocation and deallocation requests. Next is the use define allocation strategies, so for counting and grouping. So this allows the counting and grouping methods to define specific strategies for finding free blocks, and would deepen the understanding of how these strategies impact disk utilization and fragmentation. Next we have the integration of allocation methods, and lastly the GUI, which is the graphical user interface. So both are intentionally focused on command line interface or conceptual clarity. So a future enhancement could involve developing a simple GUI, while the file allocation needs to provide a more holistic view of the file system. So by the conclusion itself, the file size sim is an effective educational tool that demystifies free space management techniques in operating systems. It provides an interactive code-centric simulation of bitmap, linked list, grouping, and counting methods. Bringing theory with practice, our collaboration effort resulted in a well-organized and modular code base. Through direct integration, user gain insight to this blocks management, utilization, fragmentation, and overhead file sim. Offers a tangible platform for students, especially those in computer network and security. So we anticipate this simulator will significantly aid future computer professionals in their learning. Now, I would like to express our sincere gratitude to you, Doctor, for your invaluable guidance and support toward the development of this project. Thank you very much for allowing us to share our thoughts and creating this wonderful project. So for the reference of itself, we have a video tutorial of how the operating system works to get the basic understanding aside from your lectures. And lastly, a book, A Reset Itself, about operating system concepts from Wali Global Education. That would be all. Thank you very much, Doctor, for your time and your effort towards the class. We really appreciate it, and let us hope we can see you again next semester. And goodbye, Doctor. Thank you very much.